Hello everybody, hope you all are well. I am Manoj Pine. Today we will discuss on tidal energy. Tides are periodic changes in sea level caused by gravitational effect of the sun and the moon in conjunction with the rotation of the earth. As a basic principle, when the moon or sun is overhead of a specific portion of the ocean, the water attracted from elsewhere due to gravitational force, and thus the sea level rises up in that region and drops down elsewhere. When the moon or sun is right underfoot, the situation is similar. So there are high tides when the moon is overhead or underfoot. Since the distance between moon and the earth is much closer than between sun and earth, the gravitational effect of moon is much more significant than that of the sun on earth, despite of their tremendous contrast in mass. In most cases, the moon is dominant factor in tides. Therefore, there are generally two high tides and two low tides per day due to the rotation of the earth. The tidal energy has two forms: the dynamic energy of the sea currents and the potential energy due to the change of water levels. The dynamic energy can be made used by turbines in the tidal stream system analogous to wind turbines. Due to the high density of water compared to air, the density of dynamic energy of water flow is much higher than air flow. Therefore, the tidal turbine is usually smaller than wind turbine and can work at a lower flow velocity. Like wind turbines, tidal turbines can be divided into two major types. The first one is axial turbines. They have rotary blades with the axis parallel to the flow direction. The second type is termed as cross turbines. The axis of the turbine is usually vertical and the turbine can be driven by horizontal flow in all directions. Now one question arises: are these tidal technologies economically competitive? Tidal energy technologies have advanced considerably over the past few years, and there are a number of ongoing full-scale demonstration projects. Horizontal and vertical axis turbines currently use blades that are positioned either in parallel, that is horizontal, or perpendicular, that is vertical, to the direction of flow of water. The turbines are similar to designs used for wind turbines, but due to the higher density of water, the blades are smaller, turn more slowly than wind turbines. Furthermore, they have to withstand greater forces and movements than wind turbines. Tidal range technology has a number of options for power generation. Firstly, one-way power generation at ebb tide. A reservoir is filled at flood tide through sluice gates or valves that are closed once the tide has reached its highest level. At the ebb tide, the water in the reservoir is released through the turbines and power is generated. With this single cycle, power is generated for only 4 hours per day. The second method is one-way power generation at flood tide. At flood tide, the sluice gates are kept closed to isolate the reservoir while at its lowest level. When the tide is high, the water from the sea level flows to the reservoir via the turbines, thus generating power. The disadvantage of this cycle is that it has less capacity and generates less electricity, and it may be ecologically disadvantageous as the water level in the impoundment is kept at low level for a long time. The third method is two-way power generation. Both incoming and outgoing tides generate power through the turbines. This cycle generates power for 4 hours twice daily. However, reversible turbines are required. Tidal lagoons are similar to tidal barrage. except that they are not necessarily connected to the shore, but could sit within the ocean. Environmental impact assessments of proposed tidal lagoon in Savanessa Bay suggest that lagoons would have lower environmental impact than tidal barrages. A new type is ultra-low head tidal technique. This is a new application under development which is focused on harvesting energy from low head tidal differences of less than 2 meters. The use of tidal fences would consist of a number of individual vertical axis turbines that are connected to each other within a fence structure. The fence itself could be placed between the mainland and a nearby island or between two islands. These applications are in their early stages of development and there are no prototypes being tested in water at present. Hybrid forms of tidal energy can be found in the form of multi-purpose platforms where both tidal current and tidal range technologies are used for electricity generation. These platforms are in an early development and innovative stage. Another technical aspect for tidal current technologies is their deployment in the form of farms or arrays. Individual generator units are limited in capacity. Therefore, multi-row arrays of tidal turbines need to be built to capture the full potential of tidal currents. However, turbines have an impact on the current flows. So, the configuration in which they are placed in a critical factor to determine their potential yield and output. Tidal current technologies can also be used to generate electricity from ocean currents. Ocean currents, although slow, are a continuous flow that can provide a steady production that is not driven by the tidal cycles. Although there are currently no ongoing projects, studies have been widely undertaken while discussing on economical viability of tidal power projects. We must understand what are the barriers of such projects. Cost estimates are projected to decrease with further deployment. Estimates from across a number of European projects for 2020 has been studied. The costs are very site specific and the costs for both tidal range and tidal stream technologies can fall by up to 40% in case where they are combined and integration in the design and construction for existing or new infrastructure. Now let us understand that how to calculate the energy in tidal power projects. In the image you can see the barrage. Left side of it that is ocean and the right side of it that is basin. Let us suppose the area of that basin is A. Now let us consider an incremental volume of water whose height is dz. So the volume is Az dz. If we consider that the density of seawater is rho, then mass of that incremental volume is rho Az dz. Now the potential energy possessed by that incremental volume of water is rho Az dz into G into Z. So the energy possessed by the water stored in the basin is EF rho G integration limit Z equal to 0 to R Z Az dz, or we get A rho G R square by 2. The calculation is self-explanatory. Here R is the range of tide. Now let us understand the important components of a tidal plant. First one is barrage, which is required to form a basin. The barrage should be constructed by the material available at site or from a nearby place. Barrages for tidal power projects have to withstand the force of sea waves. So the design should be suitable to site conditions and to economic aspect of development. The rockfill dams or barrages are preferred due to their stability against flows. The barrage crest and slopes should be armored for protection against waves. The second one is sluice gates in the barrage for flow of water from sea to basin and vice versa. Tidal power plants operate on continuously varying difference in the level at which the basin must be filled from the sea or emptied to the sea, as required by the operating regime of the power plant. And the third one is a powerhouse equipped with turbines. The energy potential in tidal power development is exploited from low to very low heads, for which large size turbines are required. If the water head is more than 8 meters, a propeller type turbine is quite suitable because the angle of blades can be changed to obtain maximum efficiency while the water is falling. Now let's discuss different advantages of tidal energy power plants. Firstly, there are multiple functions. These types of dams by necessity tend to be very long, even 30 to 60 kilometers, which is significantly longer than current coastal structures. However, a long dam can function with multiple purposes such as land reclamation, connections between the islands, mainland coastal protection, and deep sea and liquefied natural gas ports. The initial investment costs could easily be shared between these different industries, thus helping to lower the cost per kilowatt hour and create higher return investments. Tidal power is predictable. The moon is not going anywhere anytime soon, which means that this type of tidal power will be found indefinitely. Furthermore, the tidal cycle is predictable and a repetitive, which allows us to know exactly when and how much power is obtainable. Available tidal power is firm as there are no wet or dry years, no dry or wet months, no influence of summer or winter on the availability of tidal energy. It is free from pollution as there is no greenhouse gas is ejected during the production of tidal power. Tidal power is inexhaustible and a renewable source of energy as the water is not going to be vanished from the earth. Tidal power plants do not require valuable land because these are located on the sea source. Tidal power, when used in combination with thermal plant, can meet effectively the load demand. After the capital cost of a tidal power scheme is paid off, the cost of power generated is very low. Though so many advantages are there are some disadvantages also. Firstly, the tidal power plant output varies with the variation of tidal range. Secondly, tidal power supply is intermittent. You cannot get power throughout the day. Capital cost of tidal power plant is not economical when compared with the conventional sources of energy. So, this is all for today. With this, I Manoj Pain signing off. We will meet shortly. Till then, bye bye. Take care.